is Jesse, and I'm here to present SpanBERT, improving pretraining by representing and predicting spans. So this pretraining method is actually an extension of the more famous one, BERT. So before we get into SpanBERT, we'll talk a bit about BERT. First, we'll talk about the pretraining tasks and the objective function BERT tries to optimize. Then we move on to SpanBERT, talk about the masking schemes and what it did different from BERT. Then move on to the experiments and conclusions. So what is BERT? BERT stands for bidirectional encoder representation from transformers. So what it uses is some bidirectional method to understand what a word represents in a sentence, right? So take any of these sentences, let's say this one. If BERT wants to understand what born means in this sentence, it tries to understand it from the context on the left side and the context on the right side, right? Then it was also built on the transformer architecture. The transformer architecture is also a famous paper. It uses self-attention mechanism to kind of weigh the importance of each token in a sequence, right? So Jesse was born in Ghana. The most important tokens would probably be Jesse and Ghana, because in a way, Jesse in Ghana kind of makes more sense in the sentence that was born in. So these are the objective functions in BERT, is the max language model and the next sentence prediction model. So what is the max language model? The max language model tries to, what BERT does with this is it tries to predict some max words in a sentence, right? So given this sentence, if you max, let's say was, right? BERT tries to understand the context of the left and the right side. So guess what this word is supposed to be in the sentence. And the way it samples these words to max them is to use 15% of the entire sequence, right? So 80% of the time, it uses the special max token to max the words, tokens. And 10% of the time, it uses any random token to replace the was. And 10% of the time, it does nothing to the word was. So going on to the second objective is the next sentence prediction. So what BERT does is to predict if two sequences that are sampled from the corpus directly follows each other. So first, it samples the first sequence, right? And 50% of the time, it samples the next sequence that directly follows the first sequence. And the other 50%, it samples any random sequence from the corpus, right? So the task is to predict if the sentence follows. It makes sense. So in summary, BERT optimizes the max language model and next sentence prediction objectives by maxing word pieces uniformly at random in data generated by the bi-sequence sampling procedure. And what you have to note here is this word piece. It's actually a tokenization technique. Yeah. So let's say this word plain. BERT would tokenize this with word piece by creating subwords. So instead of saying plain is just a token, it would rather slice it and make plain one token and ID another token. And although BERT is great in doing a lot of NLP tasks, it kind of falls short. It's not that bad, but the authors of this paper thought models, they could develop something that would be better than BERT, right? So what they thought was BERT wasn't really doing well on span selection tasks. And this is what they tried to do differently. So instead of maxing random tokens in a sentence, right? they rather mux random spans of tokens. By spans of tokens, I mean words that are continuous in the sentence. So BERT would maybe mux love and maybe watches, but SpanBERT is saying we should mux, if you pick love, if you want to mux love, then we should mark tokens that are contiguous, that will follow each other. So they would rather mux this and this than mux any random token in the sequence. Then he also took out the next sentence prediction tag and introduced its novel idea, which is the span boundary objective. We'll take a look at what these two are.
I have a question. What does the word span mean in this context? Because for the sentence that you have, Jesse loves sports, why would you not also mask the word it? Why would you also?
Span in this context is words that follow each other.
Oh.
So a set of words that follow each other.
So mask the two adjacent tokens?
Yeah. So their maxing technique is similar to BERT's maxing technique, but what it did differently is what I said. They max spans instead of random tokens, and they use this geometric probability thing to kind of select the length of the span that they want to max. Right. This is actually skewed towards shorter spans. As you can see, the mean of the length of spans they max is 3.8. And during their experimentation phase, they used these probabilities to test which one was best, and it appeared at 0.2 actually gave them the best results when they're picking their spans. And the most you could actually mask is set to 10. That is, I think BERT is 10 always, but they made it dynamic. And for the span boundary objective, so this involves predicting each token of a max span using only the representation of observed token at the boundaries. So looking at this sentence, if SpanBERT says L is 2 and it maxes love spots and love spots, right? It would take the transformer encoding information from the Jesse, and it would also take the transformer encoding from key, right? Then if you want to predict what love is or what the max, this is max, right? If you want to predict that this max is actually love, what it does is the transformer encoding from Jesse, the encoding key, and also the position encoding from the word, the word loves, but it's actually masked. So, and it passes this through the two-layer feed-forward network using the GELU activation function and layer normalization. So this is how it looks like. And the GELU is actually is kind of similar to the ReLU and the ALU that we learned in, I think, our first two classes, right? So what it does is to allow the model to learn some complex representations in your data, right? Then the layer norm kind of helps them, it helps in creating stability for the model, right? So during backpropagation, the gradient don't blow up. Yeah, so what it does, it doesn't do this. I think this is the same thing that BERT does. It uses cross entropy laws to learn. So if it optimizes this, then it means that the model is learning properly. And this is how GELU compares with ReLU and ALU. So from the original paper of GELU, they show that on some tasks in NLP and computer vision, using GELU actually performs better than ReLU and ALU. And it's actually a popular choice in transformer-based models like BERT, GPT, I think Albert as well. So if you remember correctly, I said a next sentence prediction task samples two sequences and checks if the second sequence is a direct continuation of the first sequence. So BERT conjectured that doing such thing would probably bring some kind of noise to what you're trying to do, because it is trying to mark continuous bumps. So if, let's say, the second sequence is from a random point in a corpus, and the marks is so long such that it marks this from the first sequence and the second sequence, the context that I would take from the boundaries may not really make sense, because one is from a different sentence and the other is from a different sentence. Right, so that is what it taught. So conditioning on often unrelated context from another document add noise to a Max language model. And also the model benefits from longer full length. So instead of sampling two sequences, they just sampled one very long sequence. And it could be as long as 512. So this is a BERT architecture. If you take this simple sentence, it marks as an American football game, right? And it takes the transformer encoding information from the two and the words, and yeah, it does it like this. So this is the words. This is the two. So if you want to predict what X7 is supposed to be, it's predicting that it is a football. So this is what it would actually do. So this function passes it through the two-layer fit coordinator. Then it optimizes the prediction using the so yeah, now we move on to the tabs that SpanBERT hopes to improve on compared to vanilla BERT, right? And these are SPAN selection tasks. So question answering tasks is when you give the model some passage and a question, the model is supposed to give you an answer based on the passage that you've given it, right? And Coreference Resolution is also a task that kind of it groups entities that refer to the same thing. So in this sentence, it would group Jesse and he to refer to the same person. Then we move on to relation extraction. So relation extraction is also a very difficult task. It tries to learn the relationship between a subject and an object in your sequence. So in my second sentence here, Jesse was born in Ghana. It would try to learn the relationship between Jesse and Ghana, and would probably predict the place of birth. That is the relationship. These are the baselines SpanBERT tries to compare its novel idea against. So they use the vanilla BERT and they re-implemented BERT. So what it did was, like I said, they use a different maps at each epoch. BERT actually uses 10 maps at each epoch, and they also removed all short sequences. So BERT was using a sequence up to, I think, 128. Then, so they took that restriction off and allowed the model to sample up to 512 length, right? And also in this one, BERT one sequence, they took out the next sentence prediction objective that is not BERT. So when it talks question and answer talks, SQUAD is one of the famous benchmarks in evaluating language models based on question and answer. So looking at this, you will see that SpanBERT exceeds their implementation of BERT by 2% and 2.8 8% on squad 2. And I mean, if it's surpassing tier implementation, then obviously it's better than the vanilla BERT by 3.3 and 5.5% respectively.
What are some examples of some of the experiments in the squad?
Some of the examples.
Yeah. The things that they did, like in squad, like what kinds of questions and answers, like.
So I'm not really sure about how the data set looks like. What squad from the general data I have, squad is more like I think that it was data collected from human perspective. So they just put out a passage, they put out a question, and they just want to see if you could learn the answers to that question from the passage. So I mean, you could think about anything, but I don't really know the content of squad. I've not looked at it before.
But
And then,
what language is this?
yes, English, yes. And I think they did application test on Chinese, but I'm not really sure how the results was because they didn't really publish the results from that. Yeah, another benchmark for question answering is the MRQA benchmark. So the performance here is just F1 scores. And you can see that on average, there's a 2.9 increase, right? If you compare it with BERT. Another difficult task in SPAM selection is Coreference Resolution task. And I mean, it's very obvious that most of their F1 scores is below 8, so it's a difficult task. But what they notice is that SpanBERT performs exceptionally on these tasks because their pre-training model now has the state-of-the-art results in Coreference Resolution tasks. And the relation extraction tasks, these two are actually the state-of-the-art results in currently. And from the experiment, it outperforms BERT's performance, and they realize that it comes close to the state-of-the-art results in the BERT EM plus NTB. So this is one of the benchmarks that really test language models on their ability to understand a natural language, right? And it's a general language understanding evaluation. So it had some weird tasks. Let me say a few of them. So one, like the QQP, which the task is to identify semantically equivalent sequences, right? And the MRPC, the task is to identify if two sentences are paraphrases of each other. So these tasks are very difficult, but it is something that humans kind of know, right? So their performance on this is okay if you look at it from the accuracy point of view. So MRPC, so the first one is the F1 score, the next one is the accuracy. So I think they did pretty well compared to like BERT, except on the SST2, which is the task is to predict the sentiment of a sentence. And it's not really that far away. I think they're doing really well. And they performed ablation studies on their two objectives. So the maxing scheme and the auxiliary objective, which is the SBO. So in the maxing scheme, the first one is actually BERT's maxing scheme, which uses subtokens. It maxes subtokens, right? The last one is a SpanBERT one. And so these three are linguistically inspired masking schemes. So the sampling in the Coreference is similar to what they did in BERT. They take the sample 15% and perform their masking on. But for the named entities and the noun phrases, I think the sample is 50%, and they perform the masking technique on it. And looking at this, you can see that SpanBERT performs better in all except this. But this is because it is using the NSP objective. SpanBERT was built. I mean, their novel introduction was to take out the NSP because it introduces noise, right? So if you are using it, probably respect the Coreference, you expect it to do better there. So on the auxiliary objective, they wanted to, based on their hypothesis that the two sequence sampling introduces noise, this was a test to prove that their hypothesis is correct, right? And looking at this, you can see that when they use one sequence, the performance on all tasks is actually better than when you're using two sequences. And it's even better if you add a span bandwidth objective. So in summary, BERT marks full words, not subwords, as in, SpanBERT marks full words, not subwords, as in BERT. And it also optimizes the span bandwidth objective in addition to the max language model using a single sequence data pipeline. And from the experiment, it performed best on extractive question answering task. And their single sequence training works considerably better than bi-sequence training with NSD, as seen from the ablation studies. These are references from the papers. Thank you.
Explain the position.
I can't hear you.
So, and the model BERT, so there are three. So to represent token, there are three. One is the embedding, and another is position, and another is the type.
Okay, come again.
So you mentioned about the position.
Yeah,
So when we encode a sentence, so there are three types of embedding. So, so how in a SpanBERT, how position embedding
sure, I understand the question. But from SpanBERT, transformer-based models, they don't really know positions of tokens in a sequence. So SpanBERT adds position embedding to kind of give it then the idea that this is the position where you are trying to predict appears in the sequence.
I think transformers do have a positional encoding, but the way that they compute the positional encoding, it's done in different ways, I think. But I don't.
What do you mean by position? Know the order of the word sentence.
So the position encoding here is the order of the words in a sentence.
Yeah, so I think with the tokens and the transformer, there is a numerical value attached to each token that indicates its position.
And that is the importance of the word. So that's what it does. Is I think for each word it kind of outputs a key thing. So this is basically it passes it through some sort of box, right? This is the direction of the key, then multiplies the base. So the value that comes out of this is actually how important the word is in the sequence.
What are your using?
It's a key value query this.
What is that?
The query, the key and value vectors, the transformer produces for each word in a sequence.
Any other question?
So the key would be the number of like the word, so like maybe like the word was has like a key value.
Yeah.
And the value just outputs that, so like if the key value returns 7, and maybe 7 was, that returns 7. Like
But
was.
it's not a scalar, it's I've forgotten the dimension, but it's a vector that kind of represents what was is.
Thank you. Let's start.